Good afternoon, all of you. Can you hear me? Okay. Can you see this page which I have shared with you? Okay. Okay. So last class we discussed finite field structure, and that I shared with you also. So I expect that you might have gone through that in case, because this particular thing you will not be able to understand only by reading. You will have to actually do mathematical work, right? So whenever I'm discussing this polynomial thing and everything else, uh, you should keep studying it with by doing calculations, because if you do the calculations on your own, then only you will be able to uh, implement you will be able to understand it properly, right? So in the finite field structure that I discussed, just a minute. Okay. So in a finite field structure, last topic which I discussed was uh, this how to find a multiplicative inverse of a polynomial with respect to in a Gaussian field, right? So in a Gaussian field example, this I gave you, I discuss with you and ask you to do this calculations or verify these calculations, right? So x raised to phi inverse, we want to find x raised to phi inverse. So I will discuss this once again, and then we will go ahead with the remaining part of this discussion. So in a Gaussian field 2 raised to 8, find x raised to phi inverse with respect to mode, and mode value is this prime polynomial, that is x raised to 8 x plus x raised to 4 plus x raised to 3 plus x plus 1. Now this one is a prime polynomial, okay, and we discussed that whenever we have Gaussian field, we have this prime polynomial, right? So we will be using this. So we want to find x raised to phi inverse, and this is the method is similar to the one which you used in finding inverse in Euclidean or modulus calculus, right? So in mode 26, how or z12 or z10, right? So modular arithmetic, how you find the inverse, that is Euclidean algorithm. So here also our modular arithmetic is there, right? So here the only thing is that it is a polynomial. So we have to apply the same algorithm. So our R1 is with respect to is what? With respect to is this prime polynomial, okay? And whose multiplicative inverse you want to find? That is x raised to 5. Okay, so what we do, we divide this r1 by r2. Okay, so this is r1 and this is r2. So r2 and so if we want to divide this, we want actually x raised to 8, because we have to cancel out this, right? So that we can reach to the solution. So x raised to 5 multiplied by x raised to 8, right? So the power becomes addition. So x raised to 5 plus 3, 8. So what remains is this. Okay. Now this becomes our remainder, right? X raised to 8 power is cancelled out. So this becomes remainder. So this remainder we are keeping over here, right? So at that time our Q value is this. Okay. Just a minute. I'm using a different tool so that I can highlight it. Okay, can you see this slide? Is this readable or it is small in size? Okay. So in that case, I will go ahead with the same file. Okay, doesn't matter. Okay, so now see, as per the Euclidean algorithm, again the same method, R2 becomes R1 and R becomes R2. So now our R1 is x raised to 5 and R2 is x raised to 4 plus x cube plus x plus 1. Okay, so now if we want to perform this division, we multiply this polynomial with x so that we get x to the power of 5, right? So then we cancel out this cancel out becomes, because here we do addition and addition is XOR operation. Okay, addition is XOR operation. Okay, so because addition is XOR operation, x raised to 5 gets cancelled out. So what remains is this. Now again, if we multiply it by 1, then the x raised to 4 gets cancelled out. So what remains is x raised to 3 plus x square plus 1. So this becomes our remainder. Okay, so x becomes our q and x cube plus x square plus 1 becomes our remainder. Now, sorry, x plus 1 becomes our q and x raised to 4, uh, x raised to cube, x raised to 3 plus x square plus 1 becomes our r2, r. Now, r2 becomes r1 and r becomes r2. So, our next r1 is this and r2 is this. So, we divide this x raised to 4 plus x cube plus x plus 1 by x raised to 3 plus x square plus 1. So we multiply it by x. Okay, so if we multiply it by x, then we get x raised to 4 plus x cube plus 1. So when we perform XOR operation, these two terms gets cancelled out. Remember that every time we calculate this R1, R2 and R, we also calculate T1, T2 and T, right? So in the first step, our T is T1 minus QT2. So in the first case, 0, 1 and T is x cube. right? So because 0 minus 1 into Q, and minus is actually XOR. So we take plus. Okay. Okay. Now, second, so T1 becomes T2 and T2 becomes what is T, right? So 1 and x3. So 1 minus Q x3. So that is 1 is 1 minus Q. Q is x plus 1 into x3, x raised to 3. So minus becomes plus. So 1 plus x raised to 3 plus x raised to 4. So x raised to 4 plus x cube plus 1. That becomes our t. So when we shift it over here, and finally when we perform the last operation where we get r1 equal to 1, at that time our t1 becomes x raised to 5 plus x raised to 4 plus x cube plus x. That is shown over here. So x cube minus x raised to 4 plus x cube plus 1. Now this minus becomes plus because this is XOR. So in XOR, we have both the signs are same. So x cube plus x into x cube x raised to 4 plus x cube plus 1. So this results into x raised to 5 plus x raised to 4 plus x cube plus x. So this becomes our T1. So when, as per Euclidean algorithm, when you have R1 equal to 1, at that time, what is T1's value? That becomes our uh, multiplicative inverse. So this is the method of finding multiplicative inverse. And we apply the same method. And what we get is x raised to 5 plus x4 plus x cube plus x. Is that clear to all of you? Is it understood? All of you have understood this? Yes, Priyank, is it clear to all of you? Okay, others, please respond. Okay, okay. So because now it is clear, so we can move to the next part of AES. So this topic was fundamental for understanding AES. So now we move ahead in our AES discussion. So as I told you, AES is 128-bit block encryption algorithm. There are three versions, 10, 12, and 14 round with key size of 128, 192, 256 bit. Round key is always 128 bit. Okay. This is the structure pre-round R1, R2 up to RNR. So this could be N 10, 12, 14. So NR plus 1 into 128 bits. This is the concept of byte. Okay, let me revise it. So this is the uh, typical ES cipher. Now this is very important information for you. I already discussed with you. So byte is represented by this single dimensional matrix B0 to B7. So it can be written as row and it can be also written as column. Okay. So this is what we should understand. This is row or column. So word is 4 byte B0, B1, B2, B3. That becomes our word. Again, it can be represented as row or a column. And block is 16 bytes. So B0 to B15, that is 16 byte, right? So we have 16 bytes. And how to represent them? So we have state. So state is S00, S10, S20, S30, S01, 11, 21, 31. And similarly, so S00 increasing column number and here increasing row number, right? So this way we have S33 as 16th element. Okay. Now, next, this is block to state and state to block transformation. So you can see that the state has B0, B1, B2, B3. Okay. And block and subsequently, like, so the method is this. Okay. It is like this. Okay. So we can represent it like that, insertion and extraction flow. Now, this is the example we took. AES uses a matrix ZZ. So we want to take 16 byte. Okay, 16 byte. 16 byte. So how many bits? 16 bytes are how many bits? Yes. 16 bytes equal to how many bits? Please respond. 128. 128, right. Right. So this means this is our block and we want to encrypt this block. Okay. So what we are doing is we are representing each text with hex value, because hex value has two digits. One of the digit is row, another is column, and that we take to next for the next step, that is substitute byte. So this is the structure of each round, and you can see that the state is given to sub byte process. It converts or substitutes bytes, right? So sub byte means substitute byte. Then it produces another state after substitution. Then it performs shift row and it produces another state. And then it performs mix column. And then it produces another state. And then it performs add a round key. So our round key is added at the fourth step. So each round contains four steps: sub byte, shift row, mix column, and add round key. In this sub byte, we need the concept of Galios field, and that is why in the previous lecture I explained you the whole concept of finite fields, okay, and Galios field and the polynomial operations which we studied. So it will be used over here, okay. So one add round key is applied before the first round, that is pre-round, okay. And the third transformation, that is mix column, is missing in the last round. So now we discuss substitution, right? First step, that is substitution, permutation, mixing, and key adding. So first we discuss substitution. So you can see that this is a state and this is a sub byte. Now sub byte in a table. So this is row, this is column. Okay. So A16, B16, row column, right? So we have to convert this state into another state, and how? With the help of table, substitution table. So this is the sub byte transformation table. Okay, this is sub byte transformation table. So you can see this is row 0, this is column 0. So what is the value? 63. So when we have in our table value 00, that is substituted by value 63. Okay. Similarly, if we take the table value 63, it is going to be substituted by FB. Okay. What will be the corresponding value for 50? What will be the corresponding substitution value for 50? look at the table and write. Yes, 5 3. Yes, you have understood. Very good. So we have this type of table that is of 16 cross 16. 0, you can see the columns 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A, B, C, D, E, F. So 0 to F, that is 16. Similarly, row 1, 2, 0, 1, 2, 3, 4, 5, 6. And in the next slide, we have 7 to F. So this substitution table is 16 cross 16 table. So we have to map row versus column, right? So this value C6 is replaced for the row C and column 7, right? Column 7. So the value substitution value is C6. Okay. Similarly, there is inverse sub by transform table is also available. So for the decryption purpose, it is required, right? So we have invertible table, right? So if you look at in this inverse table, what is the corresponding value for 63? Find out. If the input hex value is 63, what is the output value from inverse substitution table? 0 0. Perfect, Deep. So you can see that what we found here is for 0 0 the value is 63, right? For 0 0 the value is 63. So for in inverse table, if you see 63, it gives you 0 0. Okay, this is 6, this is 3. Clear? Right. So similarly, whole table is prepared. Now what we do, we now discuss this sub-byte transformation, right? Now I go back to the previous discussion, right? So this one. So we have a state, and so what we are doing is that we have written this 0 4 12 14 0 4 12 14. So we have written in this direction, right? Then 0 4 12 14, then 12 14 12 4 12 0, then 0 C 0 0 13 11, and then 0 8 23 19 19. So we have written column wise. So these values are written column wise. Okay. Now we take first value, that is, let's say 12. So if we want to perform substitution of 12, right? So what we do, we see one row number 1 and column number 2, right? So this is what I already explained to you. Now see, if we take first value 0 0, and if we look at this table, if we look at this table, 0 0, so the value which we are getting is 63. Now if we take 12, okay, so if we take 12, what is the corresponding value? 1 2, right? So this value is C9, this value is C9, right? So here we substitute with C9. See, have you understood this? This way all values are substituted. Is that understood? All of you have understood this? Please respond. Okay. Now there are steps how this value is not arbitrarily coming. There are methods, and these methods, here we need the use of Galileo's field. Okay. So for each byte of the state, say SRC, We have to perform these three steps, right? First step is find multiplicative inverse of SRC with respect to Galileo's field. Okay, this is our Galileo's field. So SRC inverse we have to find. That is the first step. So whatever is the byte value, its inverse we find. Then second step is we pre-multiply this inverse with matrix X. X is some constant metric that we already have and that is invertible. So we perform the operation of X dot SRC inverse. Okay. And then third step which we perform is XOR and XOR with D. So X dot SRC inverse XOR D. And here D value is taken as 63H. Our first value 00 is 63H. So here the value taken is 63. So finally, our Y value is X dot SRC inverse XOR D. Now, is this a non-linear, right? So sub-byte is non-linear transformation. What is the meaning of non-linear transformation? Can anyone say? Can anyone say? What is non-linear? In the DES discussion, I explain you non-linearity. Non-linear transformation means S X XOR Y is not equal to Sx XOR Sy. Okay. So if we find at least one such element, one such pair for X and Y, for which X S of X XOR Y is not equal to Sx XOR Sy, then it is considered as non-linear, right? So is this a non-linear? So if we take this first example S00, suppose we take S00. So suppose our R equal to 0 and C is equal to 0. Suppose X and Y equal to 0. So what happens? S0 plus XOR 0. Okay, S0 XOR 0. 0 XOR 0 is what? 0. Right? So our LHS becomes 0. S of 0, 0. Right? So if we can write like this, S 0, 0. Okay? We want to prove that it is not equal to S 0 XOR S 0. If we can prove this here also XOR, if we prove this, then it is non-linear and it can be proved easily because X 0 XOR 0 is 0, 0, and in the table if you find sub-byte of 0, 0, it is 63. Okay, so LHS is 63, but RHS equal to S of 0, okay, that is 0, 0 XOR 0, 0. Okay, so that is 0, 0. So on LHS we get 63 hex and on RHS we get 0, 0. So our equation is proved, and that is why we have found one pair for which it is not correct, and so sub-byte is non-linear. Is that understood, all of you? Have you understood this? From the table, we are saying that S00 is 63H. right? So this table that I had shown you, substitution byte. So here the value is 00, right? Understood? Please respond. Okay. So is sub-byte step invertible step? So let us see. So the answer is yes, and let us see the proof. So y is equals to x dot src inverse xor d. This is our formula. Whether it is invertible, so if it is invertible, then we can use in decryption. So what we do is in this LHS, we add XOR D. So on the right hand side, what will happen? D XOR D. So D XOR D cancels out. So this remains X dot SRC inverse. Now we multiply with X inverse on LHS and RHS, both sides. So X inverse multiplied by Y XOR D. So that is equal to X inverse multiplied by X and multiplied by SRC inverse. Now X and X inverse, both if both are multiplicative inverse of each other, then multiplication of X with its multiplicative inverse gives us identity. So this gets cancelled out. So this becomes 1 multiplied by SRC inverse. So X inverse Y XOR D equal to SRC inverse. Now, if we take inverse of this, then this inverse gets cancelled out, and what remains is this. So it means that we can find SRC if we find SRC inverse, then with from SRC we can also find the from SRC inverse we can also find SRC, right? So this is invertible. So sub byte is invertible, and that is X inverse into Y XOR D and the whole inverse, right? So this way we can find. So we need X to be invertible, right? So this X which we are taking, it should be invertible. So we cannot take X which is not invertible, right? So all the above calculations are with respect to Galileo's field. This you have to remember. Now see, why subbyte 00 is 63? Let us try to understand it. Because subbyte 00 is equals to, if we apply this formula, X is 00, SRC inverse. What is SRC? X into SRC is 00 and its inverse plus means XOR 63H D equal to 63. This we have taken. See, D is 63. So what happens is now 00's inverse is 00. Why? Because see, here we apply to find the inverse, we apply the same method as we have discussed for finding x raised to 5. 00 means all zeros. All zero means we have R1 equal to x raised to 8, x plus x4 plus x3 plus x plus 1, this polynomial, and R2 is 0. So this divided by 0 is not possible. So we have already found R2 equal to 0. So at that time, what is T1? T1 is 0, right? So T1 is 0, R2 is 0, T1 is 0. So 0, 0 inverse is 0, 0, H, right? In Galileo's field also 0, 0's inverse is 0, 0. Okay. So here instead of this inverse, we write 0, 0, H. And so X multiplied by 0, 0 is actually 0, right? Anything which is multiplied by 0 is 0. And so 0, 0, H XOR 63H that is 63. So we find that a sub byte 00H is 63H. Is that understood? Please respond. Have you understood this? Okay. So now let us calculate this find sub byte 0CH. Now you can see for 00 we have found. Now for sub byte 0C we find the sub byte. Okay. For this state, for this byte, we find substitution byte. We will substitute this value with which value? So you can see this example, find sub byte of 0CH. So the first thing which we have to do is to convert this hex into binary. So zeros, so 0 in hex is 0000 in binary. And second is C. C means what is the decimal equivalent of C? 8, 12, right? So 0 to 9, 10, 11, and 12, A, B, and C. So that is C is 12. And what is 8421 equivalence of 12? So that is 8 and 4 both becomes 1. So 1100. Clear how we have written this hex into binary? Okay. So now we have to convert this binary into polynomial because we have to perform the Galileo's field operation. So x, now this is x raised to 0, this is x raised to 1, this is x raised to 2. X raised to 2 multiplied by 1, that is x square. X raised to 3 multiplied by 1, that is x cube. All other elements are 0 because anything multiplied by 0 is 0. So what remains is this polynomial. So 0CH is equivalent to x cube plus x square. Is this understood? Are you able to understand this? How we have converted into polynomial? See, what we are doing is that we want to find substitution of 0CH. 0C is in hex. So we have to first convert it into binary. So it is very simple, right? So first 0 is converted into 4-bit equivalent because this can be represented by 4-bit 8421, right? One digit can be represented by 8421. Okay. So 0000 and C is 1100. Now we have to represent this binary into polynomial. This is very important step, although it is easy, but you should understand it. So what is this bits? This is x raised to power 0. This LSB bit is supposed to be multiplied by x raised to power 0. What is x raised to power 0? What is the value of x raised to power 0? That is 1, right? Now 1 multiplied by 0, what is the value? 0, right? Now, so we have to add, we have to convert it into polynomial. So we have to add, okay? Now second, as we are going from right to left, power increases. So x raised to 0, x raised to 1. Okay, so 0 multiplied by x raised to 1 is 0. 1 multiplied by x raised to 2 is x raised to 2. 1 multiplied by x raised to 3 is x raised to 3. So this way, all these four terms become 0 and so remains is x cube plus x square. So when we are saying that we want to find 0CH inverse, we are saying that in Galileo's field, In the context of Galileo's field, this has to be a polynomial of x cube plus x square. And we actually want to find out the inverse of this polynomial. Okay, so then, so we find first, to find the subbite, we first find its inverse, then pre-multiplied by x, the output of that we multiplied by x, and then XOR it with 63H. So our answer should be FEH. We will verify it now. See, let's start with the first step. First step is this, x cube plus x square's inverse. With respect to what? With respect to Galileo's field. Remember, again, I am repeating that whenever you are working in AES, we are taking Galileo's field. Okay, Galileo's field. So x cube plus x square, its inverse is with respect to this polynomial. This is the prime polynomial of Galileo's field. Okay, prime polynomial of Galileo's field. And I discussed this Galileo's field in the previous lecture. So how to find out? Again, the same method as I discussed in the beginning. X raised to 5's inverse, how did you find? So this divided by x raised to 5. Similarly, this divided by x cube plus x square. So that is the first step. This divided by x cube plus x square. Okay. So to perform this operation, I multiply this x cube plus x square by x5. So if I multiply it by x5, then the highest term I get is x raised to 8. Okay. See, x cube plus x square is not in this modulus, right? So we have to find its modulus. So we multiplied by x raised to 5. So x raised to 8 gets cancelled out and this becomes x raised to 7. So what remains is this x raised to 7 plus x4 plus x cube plus x plus 1. Again, I multiplied by x raised to 4. So what happens? X raised to 7 plus x raised to 6. So again, this gets cancelled out. This gets cancelled out. Then I get x raised to 6 plus x4 plus x cube plus x plus 1. So again, I multiply by x raised to 3. So I get x raised to 6 plus x raised to 5. So this gets cancelled out. So I get this polynomial. Again, I multiplied by x square. So I get x raised to 5 plus x raised to 4. So both of these gets cancelled out. And what remains is x cube plus x plus 1. Now again I multiplied by 1. So I get x cube plus x square and this gets cancelled out. So what remains is this. So if I perform this division with this, then I get this as a q and this as a remainder. Okay. And then I also calculate T1 minus QT2. So T1 is 0 and minus becomes XOR and XOR is plus. So Q into T2. Q is x raised to 5 plus x4 plus x cube plus x square plus 1 and T2 is 1. So this is the T value. Okay, is this first step clear? First step clear? If this first step is clear, you can easily do the second step. What becomes R1? Please tell me. What will be the R1 now? R1, you can see here. What will be the R1? Yes, please respond. Please understand that since if we follow this step, we follow the same way, second step. So our R1 becomes x cube plus x square and x square plus x plus 1, that becomes our R2. So this divided by this, we perform and what we get is remainder and quotient equal to x. And at that time, our T is this. Okay, you follow the same step. So I will leave this as an exercise to you so that it is only the same repetition of the process. And so if you follow this, what you get is finally, this is the polynomial. So in the last step, you can see that R1 equal to X, R2 equal to 1, R is 0. So when R is 0, at that time, it is copied over here, right? So R2 is 0. At that time, what is T1? When R2 is 0, at that time, T1 is x raised to 7 plus x raised to 5 plus x raised to 4. Or when R1 is 1, at that time, we have this. And that is our inverse. Okay? So, first step we have followed. Do you want me to perform all the steps, or you are able to understand this? Yes, students? Are you able to understand this, or do you want me to repeat for all steps? Yes? Respond to me. Am I audible to you? Okay. So this first step, this is clear, right? Now we have found the multiplicative inverse of this x cube plus x square by following the same method. Now we have to pre-multiply it with x. So our this value, what we have found is multiplicative inverse, right? X raised to 7 plus x raised to 5 plus x raised to 4. So first we have to convert this into binary. Okay, this is important point. First we have to convert this into binary. So how to convert this into binary? So we have to take x raised to 0 on the right hand side and x raised to 7 on the left hand side, right? So x raised to 0 multiplied by 1 plus x raised to 1 so here in this case the terms are missing, right? X raised to 0 is not there, x raised to 1 is not there, x raised to 2 is not there, x raised to 3 is not there. So x raised to 0 is 0, x raised to 1 is 0, x raised to 2 is 0, x raised to 3 is, so these are the coefficients. Okay, 0 0 0 0 are the coefficients, and x raised to 4 term is present, so coefficient is 1. X raised to 5 is present, so coefficient is 1. X raised to 6 is absent, so coefficient is 0. X raised to 7 is present, so coefficient is 1. So this we have obtained, which is equivalent to this polynomial. Okay, not this polynomial, this polynomial. Okay. So inverse x cube plus x square's inverse, that is x raised to 7 plus x5 plus x4. This polynomial's binary equivalent is this. Is this understood? Binary equivalent. Okay, so now we have to take this matrix X. Okay, this matrix X. See, first row of the matrix, if you remember, all other rows you can remember easily. First row is 1 0 0 0 1 1 1 1. Okay, now what we perform is, in the second row we perform right shift. Okay, so this one comes over here. So 1 right shift. So 1 1 0 0 0 1 1 1. Then again we perform right shift. So 1 1 1 0 0 0 1 1. Right. So again we perform right shift, and finally what we get is this. Is this clear? Understood? Circular right shift of row 1 by bit 1, by 1 bit. Clear? This step, how we have now this X value, X matrix we are taking. Okay, this has to be taken. And to remember this, it is, if you remember only one row, the remaining 8 rows, you can remember it by right shift it by 1 bit, right? So row I equal to circular right shift of row I by 1 bit. So this is okay. I got disconnected. Can you hear me now properly? Okay. So have you understood this thing? What we are doing is second step, X into SRC inverse, right? And SRC inverse is this binary value. But how we are writing it? LSB to the top and MSB to the last. So this 0 0 0 0 1 1 0 1. So if you see here 0 0 0 0 1 1 0 1. So X multiplied by SRC inverse we have to perform. Okay. This is simple matrix multiplication. This is 8 cross 8 and this is 8 cross 1. So the result is going to be 8 cross 1, right? So 8 cross 1, how we obtain? So if you see 1 multiplied by this 0 plus 0 multiplied by this 0 plus 0 multiplied by this 0 plus 0 multiplied by this 0 plus 1 multiplied by this 1 plus 1 multiplied by this 1 plus 1 multiplied by this 0 plus 1 multiplied by this 1. So when you perform this addition, remember that this addition is XOR. Okay, this addition is XOR. And so our first row is this term 0, this term 0, all those where you find multiplication with 0, those term gets cancelled out. So what remains is 1 XOR 1 XOR 1. So this 2 XOR 1 XOR 1 gets cancelled out. And so finally what remains is 1, right? So here one element of 8 cross 1 matrix is 1. First element is 1. So what we do? We write it like this here. Okay, that becomes our LSB. Okay, so in the similarly row second we get 0, row third we get 1, row 4 we get 1, row 5 we get 5, sorry 1, 0 0 0, and that we write here as, okay, that we write here as output matrix of 8 cross 1. So 1 0 1 1 1 0 0 1. So that we have written over here 1 0, sorry, we, this is our LSB. So 1 0 1 1 1 0 0 1, right? So we write like this. Okay, clear? Please tell me that you have understood. Clear, all of you? Right? So it is simple. And now what we have to do is we have to perform XOR with 63H. So we convert the 63H into binary and then we perform XOR. Please perform the XOR operation on this output value with XOR and XOR it with 63H. What is 1 XOR 1? To perform this XOR operation, okay, the second 0 XOR 1, 0 XOR 1, okay, 1 XOR 0, 1 XOR 0, 1 XOR 0. That is 1, right? So what we get is 1 1 0, 0 1 1, 1 0 1, 1 0 1, 1 0 1, 0 1 1, 0 1 1, 1 0 1. So this is our F. But this binary is equivalent to hex F, all ones F, 3, 1 and 0, that is E. So this is our sub-byte calculation, right? So this is what we have solved. Our problem was that we wanted to find this 0CH and its equivalent, that is FEH. Clear, all of you? Yes, all of you have understood? So sub-byte is invertible step and SB0CH is equals to FEH. Okay, and if you look at this table, in this, what we have found is 0C. Okay, so look at 0, 0 and C. So that is FE. So this FE is not random value. This is actually affine cipher. Okay, we actually perform affine cipher here. This is actually multiplication followed by addition. So multiplication followed by addition is actually affine cipher. Right? So we multiply and then add. So our add operation here is nothing but XOR. So this is actually affine cipher. First multiply, then add. Do you remember that? First multiply, then add. Affine cipher. Right? So this is actually affine cipher. Okay, so we add with 63H. Okay, so if you look at the table, this I have already shown you in this slide. This slide I have already shown you that if you look 0 0, it is 63. If you look 0C, it is FE. Similarly, if you take 63, it gives you 0, right? So it's invertible. This one is invertible. Now, first step is over. Remember, we have only performed first step today in our in today's lecture. We have performed first step, this find multiplicative inverse, pre-multiply and XOR. These three operations are actually only one operation, sub byte. We have only done this sub byte. Okay, we have to perform the next shift row, mix column and add round key. So these three operations we will see in next class. Okay. Okay, I hope it is clear to all of you. Please read book and refer to textbook for further reading, and I will also share this document. Please refer to the slide which I have already shared with you. so that at last moment all concepts remains clear to all of you. Okay. Thank you, all of you.